We move on to the pendulum. This is another good example for simple harmonic motion. We can analyze the problem. This is the free body diagram. Downward, you have the weight of the pendulum bob, mg. This force vector can be decomposed into a component in this direction, the direction of the string, and another one perpendicular will be tangential to the trajectory. This angle is theta. This is the same angle theta. So this component is mg cosine theta, and that component is mg sine theta. And it is minus, just like the restoring force for the spring in Hooke's law, because this is a restoring force that tries to restore the pendulum bob to the unstrained position here. So the net force that drives the pendulum in its oscillation is this, minus mg sine theta. And sine theta is equal to S divided by L. S is the arc divided by L, that is sine theta. Okay. So we have this equation for the force. For small angles, sine theta is the same as theta in radians. To check on this, if you use your calculator, when theta is 10 degrees in radian, this is equivalent to 0.175. If you check for sine 10, it is 0.174. So they are the same. Okay. Theta is small. Theta in radian is the same as sine theta. So now, in this equation for the force mg sine theta, we can replace sine theta by theta in radians. Okay. And theta in radians from this equation is S over L. That's theta in radians. So now we have this equation for the force minus mg over Ls. I want you to compare this to Hooke's law. You have the force there, the restoring force is minus kx. S and x are the same. These are the displacement from the unrestrained position. So mg over L plays the same role as k. Okay, the same role as k. So we can substitute for k, mg over L, cancel m with m. So omega equals square root of g over L. And we can go back to the equation for x for the pendulum. So now the displacement x is a cosine square root of g over Lt. This is a nice result. And one of the experiments that we'll be doing, in fact, that was in physics 1, is to measure the period for the pendulum from this equation. T equals square root of L over G multiplied by 2 pi. You can see this similarity between the motion of the mass attached to the spring and the motion of the pendulum. Maximum amplitude corresponds to maximum amplitude. Then at x equals 0, V is maximum. Here also at x is 0, V is maximum. Then when the spring is compressed maximum, similar to this situation, the displacement is maximum. Okay, the acceleration will be maximum, but the velocity is 0. Here, acceleration will be maximum, but the velocity is 0. So because of that, it pushes the mass, and here push the pendulum bob and returns back. At this position, x is 0, velocity is maximum again, and this motion repeats over and over again. So we understand now the changes in the position, in the velocity, and in the acceleration for various phases of the motion, whether it is a mass attached to a spring or whether it is a pendulum. It's the same kind of motion. Galileo was the first to notice that the period of a pendulum was independent of its amplitude. The period is independent of the amplitude. Galileo was the first to notice that and to report about it. The period depends on L and G. G is constant. If you are on Earth's surface, G is 9.8 meter per second squared. So the period of oscillation for the pendulum then depends on the square root of L. A simple pendulum is suspended from the ceiling of a stationary elevator, and the period is measured. If the elevator moves with constant velocity, what will happen to the period? It increases, decreases, or remains the same.
I think it was number 3.
Number 3.
Yeah.
Yes, thank you. Yeah, it is number 3 because it moves with constant velocity, no acceleration involved. Okay, the elevator that moves at constant velocity is very much similar as if there is no motion. Now, the same story, but now the elevator accelerates upward. So now there is acceleration, which means now G will change in the equation for the period. You have G, because of the acceleration of the elevator, there will be a net value for the acceleration. So the period now will change. And as we see from this equation, okay, when the acceleration of gravitational acceleration increases due to adding up the acceleration of the elevator, so the period here decreases. Another question. The period of a simple pendulum is measured to be T on Earth. If the same pendulum were set in motion on Moon, what will happen to the period?
It will be less than T. Greater.
Look to this equation.
Okay.
G on the Moon is 1/6 G on Earth, right?
Yeah.
So rather than 9.8, it would be there like 1.6, something like that. Okay. Smaller value for the denominator makes this greater, right?
Right.
Thank you. Pendulum doesn't have to be a string and a bob. It can be of any shape like this, okay? Or what we need is to have a pivot and oscillation around that pivot. The center of mass here defines the length of the pendulum. The distance between the pivot and the center of mass is L. And then whatever we studied earlier applies here. What we studied regarding a simple pendulum applies to this pendulum. Okay? So the period of oscillation is 2 pi, because here we have dimensions for this body, it's not a string. So deal with the moment of inertia. So it is I, the moment of inertia, divided by mgl. And for this pendulum, I is ml squared. So when you substitute for the moment of inertia, ml squared, this equation is simplified to this equation, which is the same equation that we have earlier for the simple pendulum. 2 square root of L over G. One nice application is the damped oscillations. these are the shock absorbers that we have in our cars, so that we do not feel the tiny holes or the things on the road. Okay, the shock absorber takes care of kind of problem. Simply, it makes the oscillation fades away. The amplitude goes down to 0. We have several situations. This is simple damping for the oscillation. Here we have what we call underdamped oscillation. Here we have what we call a critically damped oscillation, and here what we call overdamped oscillations. So here there is oil inside the shock absorber, okay, and there are holes in the piston, and usually it is viscous. There is viscosity for the oil, there is friction. So together this acts to resist the oscillation and to create the damping.